All right, welcome back everyone. We will now be going over problem 3 of exam 3. And we are given a bar here that is laid on a frictionless surface and is being rotated with a torsion spring. And we're given the K value of the spring constant. We are given the mass of the bar and the length. And so for part 1 of this problem, we need to write down the equation of the rotational motion in terms of mass, length, the spring constant, and theta. And it gives us a little hint here that the torque exerted by the torsion spring is equal to negative K, or the spring constant, times theta. And we'll definitely be using that. So this is very simple. We'll start with torque is equal to negative K theta, right? And so we also know that torque is also equal to inertia alpha, right? Or the accelerational, or the rotational acceleration. And this is an equation that you'll also need to know. The inertia for a bar is equal to 1/12 times mass radius squared. All right, and so now we'll basically be plugging these equations into each other, and that will give us our total derived equation with all the values that they ask for. So torque is equal to these two values, so we can say these two values are equal to each other. So we have negative K theta is equal to inertia alpha. All right, and we know what inertia is, so we're going to plug in the equation for inertia. That's going to give us spring constant times theta is equal to 1/12 m mass times the radius squared times alpha. So we're almost there. We've got K like they asked for. We have theta, we have the mass, and we have the radius, which in this case is the length. So we'll just a little denotation here. Radius is equal to the length. So we can plug that in if that helps you guys. But we have alpha here, and it does not want us to have alpha. So something that we can do, if we remember from kinematics, distance, the derivative of distance, we'll say we'll say dx, x is the distance, is equal to velocity, right? And the derivative of velocity is equal to acceleration. And we can do that for angular theta, angular velocity, and angular acceleration. So we can say the derivative of theta is equal to omega, and the derivative of omega is equal to alpha, which basically means this alpha is equal to the double derivative. So you can put 2 dots here. I like to put 2 little marks. That's what we did in calculus. The double derivative of theta is equal to alpha, and we'll plug that in here. So here I'll isolate that. So negative, oh no, I'm out of the camera view. Okay, so we'll move it over here. Okay, so negative spring constant times theta. Oh man, there's no room over there. Okay, here. We'll switch things up. We'll just slide the paper up here. So there we go. We'll do that. Okay. Negative K, which is the spring constant, times theta is equal to 1/12 times the mass times the length, which in this case is also radius. We'll say length squared times the double derivative of theta. And that is how we get our equation of rotational motion with all the constants that they ask for. And in the next video, we'll move on to part 2, where we will calculate the angular frequency, the standard frequency, and the period of motion. So I'll see you then. Thanks for watching.